Okay, uh, so this is title of my. All right, I'll start from the scratch. Galton's the famous regression toward the mean chart. I think you must have seen this many times. I don't know. Well, just curious if there are sort of mathematicians here who have not seen this. Okay, 1 minute. All right, or you can just Google it, not Google, Gemini's it will explain this much better than I do. All right, so very quickly, this is the chart for explaining the relationship between the parents and the children. And earlier in that day, there's no computers, so they have to do some very sort of human intelligence to put all the data in here, and it's too messy. So a big sort of idea is that they bing it and then chart it how many cases there are. All right, and also they scale it right so that it can be fitting into this frame. Center it, and they have a good explanation how this unit is coming from, which I'm not going to say it. Notice that on this one, it's quite different from what we thought. We usually think that the children will be sort of the Y and parents should be the X. But in those days, they just switch it around, okay? Kind of the inverse regressions I would like to mention today. But anyway, starting from this density plot, you will say it. They just bring it. This ellipse comes up, and that is the sort of birth of a lot of nice things we are talking about: bivariate normal, multivariate normal, and a lot of classical statistical analysis, all based on this keen observation. There's an ellipse here, and so if you plot those points, which are about the same, they will be centered at the same place, and it's the contoured nicely. So that's it. And he has a good explanation about what these lines are. One of them is regression line forward and backwards. The upshot of this is something he called the regression toward the mean, which means that if you have a parent which is this high, and then the children will be also higher than the median, but not as much, slightly spread back. And so if you pop this through many cycles, then eventually the mean is the destination. So that's called the regression toward the mean.
What was the sample size?
Sample size, you can just add them up. I don't know how to add, but this is the counts. Okay, I don't know, not too many. More than that. See, we got a 20 here, and this is 17, and this is more than about, I would say about 400 or so. Okay, so anyway, on I think the original at that time sort of elliptical geometry probably is very popular. So they have this nice tool to draw this beautifully and illustrating the relationship between the X and Y's. And so the modern impact of this bivariate or multivariate normal diffusion is far-fetching, and including the Stein's estimator, and that's being used in this modern sort of generative AIs using these diffusion models. There's a big areas in machine learning or AI. I remember that I was still a student of my advisor, Jack Kiefer. He has this beautiful works on, what come up in the future of the statistic. And he mentioned this classical sign estimations, and all this time, this is so abstract. Why it is important? And now we prove that he's right. So it's amazing. Okay, so anyway, I'm going to start with my earlier work on slice inverse regressions, and it's somehow directly or indirectly influenced by these big spheres, okay, or ellipse. So the framework is this. You have a model that's related x to y, and you don't know what it is. The only thing you know is that you can do some dimension reduction. So you project into a k-dimensional space, and then you can use this as a summary statistic to build up relationship with y. Okay, that's the only assumption. So how do we do that? Switch it around. Look at the y, and then look at the conditional expectation of the x, and use some assumptions, which will quickly go through it, and then you can have a simple procedure. So the procedure looks like this. You standardize the y, x, and then slice the y into several intervals, then you compute the inverse mean, and then you form the eigenvectors or eigenvalues, and eigenvector from this slice mean. The matrix comes out from this slice mean, and that's it. The upshot is that the eigenvectors are corresponding well with your original beta, although it's not one-to-one correspondence, because this holds you can do some sort of linear combination about the different betas, but the space-wise, it's consistent. Okay, so, and at that time, I call these directions as the EDR direction, effective dimension reductions. Later on, I think that starting with Dennis Cook and his students, they do not like this name of effective dimension reduction. They think it's more appropriate to call it sufficient dimension reduction. So that's become, I accept that, but I have a tiny remark about this sufficient state, because in my mind, nothing is totally sufficient. Okay, and in fact, in my earlier work, I'm aware that this direction I get cannot cover this whole thing. It's only a tiny little bit, right? Because you have a limitation on the data and some other constraint there. So I was not so ambitious to call that, well, I find this sufficient space or sufficient that. And in terms of the classical definition of sufficient statistic, it's very rigid. There's nothing called a partially sufficient statistics. Okay, you either totally sufficient or it's not sufficient.
What's your assumption there, classic, about the x given x independent of y given projections? Isn't that a classical notion?
No. The notion is not. The classical notion of sufficient statistics is more than that. It's not just the independence. Well, that's a different story. I'm not going to go into that. That is Basu and all the generation, they have very carefully defined what is sufficient and what is necessary. And so it's a jungle there. You want to interested in, you can dig into how they carefully define that. But anyway, you know, call it sufficient, that's fine. That's commonly acceptable because that's give you a vision of summarizing that the things that you called it, you know, independence condition on that. Yeah. Okay. So Chris Holder. Well, I must acknowledge that this is with the help of Gemini, right? So you could ask me to put it here, but I didn't. Watch my time. So that's one method, and later on or simultaneously, I think Dennis Cook noticed that cell will fail if there's some sort of symmetries playing around. So for example, y is proportional to beta x squared, because you can see if I condition on y, then the positive and the negative sign will cancel out. So you get 0. So this sort of the space that was captured actually is degenerate. So what do we do? At that time, I use this PhD, which is just go back to the forward region, and PhD is trying to capture the second derivative of this service there. So there's a Hessian matrix involved there. Dennis has a nice idea using the size, the covariance, which I'm not getting into it. So anyway, the upshot is that you can do the first conditional expectation, or you can do the second order, or you can do some sort of weighting. All right, so now, so all of this, there is this big assumptions there. Why it works? This is a little bit geometry there. I would say very simple geometry. When you condition on a y, if you look at the deeper, you can first condition on the directions there, and that option simply off. So if we condition on this two directions there, then taking the expectation of that, this one has to be linear. Otherwise, you cannot have a sort of one. So suppose this one has just one direction. This one, if it pop up as a curve, then one dimension, you have to leave the two-dimension thing. That becomes a headache. It's not saying that you cannot do anything, but just to simplify. So I would assume that this one will be just one-dimensional, right? So that's a big assumption. So suppose that you believe that x coming from the multivariate normal, then you use that elliptical sphere stuff. You can visualize it so that the conditional expectation is actually a straight line, and that's a fundamental assumption behind this multivariate linear regressions there. So, but so the question is that you need these assumptions, but how will I know how general that is? I do not know what the beta is, but could be anything. So I was visiting Peter Hall, and then we spent a nice time there, and eventually we justify that this is not a big assumption. In fact, that if the dimension of the X is big, and you're looking for a high dimensional project on low dimensional directions, then beautiful things comes out. Almost all the directions are approximately linear. So that is, suppose that you assume this, going back to this sort of the Bayesian framework. So if you do know what beta is coming, it's just assuming it's coming from a uniform distribution on sphere or something like that. So on that sense, we can prove that this is linear, holds almost everywhere, as long as the dimension is big enough. Okay, so it's non-trivial and early days, and very first scratch Peter about this using sort of this Edgeworth type of expansion. It's very complicated, and we've managed to make it a simple version of it. So everything do not need to do this Edgeworth expansion. It's just a beautiful device. I think it's called the rotation twin. So if you're interested in prove this, I fully recommend to read our paper. So anyway, that's the result. So things are fine. Okay, until I look at this Galton housing data and then find this ellipse. What this one shows is this. On the vertical axis, that's the housing price per zone or per census tract in Boston. Variables, there are 13 of them or 12 of them. Crime rate, house size, and sort of the percentage of poor. Very famous data. If you're interested, just Google it, it shows up. All right, so what we do is doing the size inverse regression. And then this is the pattern comes out with the first two components, shows an ellipse. Then after some variable selection stages there, well, this is the other view, you know, beautifully spinning around. So I noticed that there's a big problems in sort of the statistical modeling. So if you turn it to one view, you will see that y and that angle looks like, you know, perfectly linear. But if you turn it to another view, no, it's not. Now you are applying this multiple linear regressions. 99% of the time, you will find this directions, but not the direction. The consequence of this, these two angles have drastically different interpretation. You are choosing this angle. What do you believe is that house is directed to the physical size, housing price proportion to the size, square footage, or whatever. All right, this makes sense. But if you look at this, it's just totally different. It is a crime rate and the percentage of poor. It's a combination. Beautifully, it's one x1 plus 13 or forgot percentage of this poor multiplied beautifully together. So in terms of the modern times, we're talking about this idea, ethnical question, the fairness. Okay. Now, if you present this view and somebody comes out with, you're going to be bitterly criticized. Crime rate and percentage is most important part. Why did you ignore it? Okay, so that is a lesson. Hope that people can remember that. So this nonlinear confounding is very serious one. It's not just fun. Okay, so this is. So we have a way to do it. The first stage is that well, you still want to fit the linear, multiple linear regression. That's fine, but then you should do this nonlinearity checking. Use that as the y. Think that one is you substitute your y, and then do a slice inverse regression to do that. Then you can find that second direction spinning around there. So easy fix. So this is the things I call the helical confoundings. It's kind of the nonlinear confoundings between the variables, which has been ignored for a long, long time, and maybe even up to now. Okay. All right, so I'm going to skip this one here. So any question so far? So that's the end story of the slice inverse regressions. And you will see that why I do not want to call this slice inverse regression is finding this sufficient dimension space there is because sometimes you really don't know what is really is sufficient. In that case, perhaps you will just combine both directions there. But that's a debatable modeling issues there. Okay, so next one, I think I got to go even faster. Otherwise, I might have a trouble getting to my main part of the talk, which I think is most exciting. So let's see. All right, so the second notion is called the liquid associations. And this graph just freshly produced by my colleague Ker-Chau. I do not have this picture when I was producing the papers there. So what this one shows, this is three-dimensional object. Okay. I'm going to spin it. You see a hole there. You see sort of this direction and that direction sort of crossing, and that's the main part. See if I can start here.
This is the same figure being rotated.
Yeah, just rotate it this way. You look at this object here and you sort of here and just spin it up. All right, let's just put that on. Anyway, let me go to the next slide. All right, so this the two this is the sort of the part that we actually look at, and that's the way that we generate it. Okay, x, y following this bivariate normal distribution with some correlation following normal distribution and so on. This is another angle. You can see it. That's all right. Similar. And this is a different object. It's sort of a sheet, sort of twist a little bit. And this one is just, I don't know if it's the same or that as the previous one, but it really doesn't matter. Okay, so this three-dimensional distribution is what I'm going to use sort of as some sort of geometric concept in my mind. And actually, that's not come up on the pure geometry or any density functions I would previously conceived. But in fact, it's motivated from the study of some complicated biological data, and thanks to Steve, he's give a nice introduction, because we're living on the same old age where at that time microarray is very popular and people use a variety of statistical concepts try to digest it. And here is the concept I come up with that it has to do with the triplet. So instead of looking a pair of the gene, which was quite popular at that time, I suggest that we should look at three genes. Okay, so the idea is this. It's better to use this chart to illustrate. Let's see. Oh, it's too fast, sorry. Oh, I'm in trouble. Okay, forget about it. I missed one important slide, so. But anyway, so I'll say it here in my. So the real concept is that when we study, say the two genes, whether they are co-expressed or sort of the opposite, we have the interpretation. If they are co-expressed, means that the gene product with the protein have the similar functions. And if the anti-correlated, that means that the function are sort of counter each other. Right? Both are very important in biological, and you have to differentiate what is a positive correlation from what's the negative correlation. But compounding, the issue is that people can use this correlation to find out whether it's positive or negative significance. But they totally ignore the situation that these two genes are uncorrelated. You cannot see it. But that seems to me is very important because natures are not always positive correlated or always negative. We are not that rigid. We are very dynamic. So intrinsically, there should be a sort of a fluctuation of your serial status that's governed the role, and then perhaps sometimes you have a positive correlation, sometimes you have negative correlation, and two can cancel out. Okay, so how do we find that? So you have to imagine that there's a thing I call the controller variable or scouting genes there. And at that time, I don't think people understand what scouting genes is never being used in the genomics. They will think this probably is a mediator. So it's not really a mediator. I'll explain it to you. But anyway, statistically, we do not have this strong causal relationship implied. That's the key, right? But in the genomic world, they want to use that. Any association, they will say, oh, this must be this caused that. So this is just a way to say, show myself how to say that these genes actually drive their correlations. They are just we just as scouted, we find that it's associated. All right. So anyway, that's the idea. There's a Z which will control this or scouting this correlation change between X and Y. So how do we measure it? So that's easy. You assume that XY undergoing normal quanta transformation, then I can use this simple X times Y times Z as a measure of this, I call it liquid association. And why does that make sense? Because once you have X, Y standardized in this way, then the correlation between the X and Y is just E of X, Y. Now I want to see what's the effect of changing this product when I control the Z from the lowest to the highest. So I need to find what is this guy is and take a partial, take a derivative with respect to the Z and then average out again. All right, so that one can be estimated by this. And the assumption needed is that the Z has to be normal, right? And that's the consequence of the Stein's lemma. Okay, the application at that time, I look at this metabolic pathway is very complicated. And I look at this look at the small circles. I better, instead of looking at all this, I choose this one. So the data is actually coming from the East. There are about 6,000 genes there. So what's relevant is all the genes shows on this map. Okay, so I choose this one as my X and this one as my Y. Why? Because this called this arginine, this urea cycle. The main purpose of this is control the level of the arginine. Okay, so it has this nice loop there. Now, which means that if the body think that the arginine is needed, then they have begin to manufacture it and go this way. But when you have enough arginine, then you have to get out of it. And so this is a way up. So this gene control the sort of the back door. All right, so sometimes this one has to shut down, and this one here has to open it up sometimes. So if this one is shut down and this one is open up, then that means they are negative correlated. All right. So now if you want that, sorry, I probably just say wrong. The body needs arginine, so this one has to be shut down and this is open. Your body think that this one is not needed, and this one has to be shut down, and this one has to be coming up. Anyway, this is sort of this association change there, and that's important. And so we use the microarray function. So put this one X and Y. I want to see what is driving this correlation change. So around the 6,000 genes, the top one is this guy. This guy. Okay, sorry. It's not, I'm not using this one, but using this one as the X, right? Because the way that this arginine is doing is that you have some metabolites coming in. So this one is actually the control, okay? And this one is just the outdoor. So I'm actually using this one as X and this one as Y. Sorry, it's been done million years ago. Okay, so using this as a pair and find this one as a eighth place negative. The top one also makes sense, but it's a little bit hard to explain. It's somewhere, it's some sort of regulator stuff involved. So I just skip it and the eighth place, I'm able to find that controller. So I was quite happy with that. And also, the sign is correct. This liquid association score is indicating very well with this dynamic change there. So when the high HP2, that's on this part here, they shows the negative correlation. That's what we want. When the cell needs the arginine, and this one is just the opposite. Okay. So so that's about the liquid association study. So these are all my old stuff, and then I ask what's the challenge, right? So because I know that nobody is really using this stuff in this AI. So this is what the Gemini suggests that, well, perhaps you can do this. You and how me even try to present it as screen. Okay, so it says that well, the manual exercise diffusion problem about high stack and that, and the issue is that sometimes you have to stick with this additive, but that's just for the simplicity, but all is popular. But this is nonlinear relationship is important, and punchline is this basis confounding XAI impact score is inconsistent and so on. It's beautiful sort of advisement for me, but I still have not done it.
So this is exactly some AI output.
Oh yeah, Gemini, beautiful. You know, I'm not as good as a salesman, but well, I know some of the keywords are up there. So, and the danger consistency SDR solutions will help. So beautiful. Okay. Now there's even this. Imagine this is something source. Well, this one is I give it some hint. Okay, so it make a beautiful story. I say, hey, you may have this scenarios. The relation could be changed, and you must be able to do it. Well, anyway, just for fun. All right, so I'm beginning to talk about my transition. How many minutes do I have? 20 minutes? 25?
Done 20 minutes.
20 minutes left. Is that right? 15, right? 1 hour?
We started from 15.
Yeah.
So now it's
15?
50 minutes.
15? 1, 5.
5.
Okay. All right. I have to rush. I thought I have a full hour. No. Okay. Sorry. All right. So story is too long, but let me see if I can get this one wrapped up quickly. So this is a transition. About 2 years ago, I gave a talk, and this subtitle is that can logic becomes a trait shared by AI and human intelligence? It's quite ambitious. And what I mean, the logic is actually sort of the operational logic. It's not because you cannot tell this. I thought this is logical and this is logical. I don't see that. So what the logic means is that there should be a procedure-wise. People think it's logical way of doing things, do this and that, and the machine will agree with it, and so we can call exist. Now, even this sort of minimal requirement is not there, and that's why we are so struggled with how can they do it? How can I not do it? What's the reasoning power there? Okay, so I show you why I changed my mind, and I think that if we are sticking with how are we going to model the data, and we'll probably never get there. All right, because as you can see that this manifold is so difficult, and a lot of people have different ideas there. And even if among the experts we cannot agree with one sort of single way to do it, how can you expect that the AI will listen to one of you guys there? Right. So this is just a different way of thinking. Okay, it's all because of these things I call the statistics. Big data, this is one property I think is very important. It's highly plastic in the sense of that you can almost manipulate in a way so that whatever the result you want, they can generate for you. It's good, but it's also bad. All right? It's good means that you can design what you want, but it's bad is that if you not tell people how you design it, then it becomes a disaster. So here is the thing is that what we would like to tackle these problems and how to do it in a way so that at least people can have a common ground, agree that well, that problem is the minimal requirement that we have. Okay, so I sort of follow this elementary geometry. We need to have some postulate. And of course, we have the theorems or so on, but we'll see that what are the theorems there. It's very elementary. So from this quality engineering's viewpoint, this is what I'm thinking about. You want to have this AI product to be acceptable by everybody and think they feel comfortable. You need to have this lucid operational logic on how you design it. And that's the way you will have a high quality product. That's a minimum assumption. And we have two projects undergoing. One is called the Yo-Yo and one is Pinball. And I'll show you what they are. Okay, the Yo-Yo is easier to explain it, and I definitely can do it in 1 minute. Post training predictions, it's about less. You have this neural net, and the product is to do this label this class, okay, car or monkey or whatever. So after they extract this row of the features, is probably the 1,000 or so, then they use the softbank, they do linear combinations, and then they just put this logic and do it, and that's the outcome. The problem is that the logic here, the probability represented is always overly optimistic because of the training. Okay, when you do the training, you try to look at the best fit, and that's well-known things around, and you can see that the true this is a predicted probability, and this is the actual probability of corrections. It's not, it's vary a lot on this part. Okay, so what people do is they do some sort of isotonical regression to do correction. That's a typical way, right? But to do things like calibration, you need a set, which is usually called the calibration set or validation set that has to be untouched. But that's also poses a problem because the sample size is the issue and the quality of validation. So look, seems to us it's a good idea and it should be done. And I'm not against it. It should be enforced, but it should be enforced a rigorous way. But however, we think that there must be a way to minimizing the needs of this validation set, not totally eliminate, but try to cut down the over reliance. So here is our criticism. That is, the whole the current state of the art, this prediction, the lack of this thing, what we call the self-critic. That is, you produce your product. Before that, you should check whether this is nice, it is a good product or not. Whether this image, I'm using this trend, the feature to represent this class, it is reasonable or not. They just totally do not have that internal checking there. So you kind of mix the sort of high quality with the low quality ends there. So you have a way to cut down it. Then, at least some higher ends, let it go. Low ends, call back and do something else. All right, so that's sort of the common sense or basic operational logic there. So how do we do this self-critic? That's the things I want to talk about. So it's a design issue there. So how did you do this? So the main idea is that instead of having this feature to represent a particular class, I would like to have a counter feature there, say that well, your feature is not capturing right thing. All right. This counter features, we call the contrast fidelity, is try to capture the sort of the features, a combined feature from all other non-target classes there. All right, so it's kind of a dual game there. So one image present there, you have to evaluate not only the features that you think is that class have, but you also have to take the opposite side of it. Say, no, it's not that class, but I'm going to find another representative there and see which one is the winner. So that's the basic idea there. So you have a target utility and a contrast utility. So these are the postulates. So you cannot just simply say that well, dog should not be considered a dog, cat and other. We need to have some postulate to say that these features at least have to satisfy certain inequality. So that will be representing the features and this contrast. So this is so very simple. You think about it, this is what it should be doing. So for the target one, if you image is truly belong that class, the feature should be better, higher than those from the contrast group. That is, those objects is not belong to this particular label class. Right? So we want to have this sort of leading. So the leader of this feature has to be the meaning of it has to be bigger than the largest of those objects from the other classes. So that's a postulated one. And it's sensing on the C. So yeah, this is contrast, so you just switch it around. So these two nothing. Now, the most important part, and this in fact will bring out some nice geometry there, is this, we call it the cross channel. Okay, the minima T value for any target group must be greater than the maxima C channel value for the contrast group. Why do we need that? Because that each X, you will have the two values. One representing the target feature. One is this control target feature there. And the higher one will be representing this label to compete with other classes. So if you do not have this relationship, then you have a trouble. That is, images may not really belong to this target group, but they will take over as the representation of this class. So that's going to be creating what we call the catastrophic representation. So it looks like somebody steal your ID and pretend, hey, look like you. That's sort of the things there. So this is the most important part. The other two are kind of easy to understand. And this one brings up a nice geometry. That's what you say. Okay, so remember that we have this K class, then you have to present the K traits, right? You have to combine it, and we have to have this minima and maxima. They have to be set up together, so this ensure their exchangeability. Okay. So all together, we have this P channel order, C channel order, and this cross channel order, and this cross plate exchangeability, because I do not want to have a particular plate standing out against the other. So this all looks like a postulate. I think people will, any customers will be happy to accept. It does not impose any complex inequality using sort of information matrix, feature information, or such as no modeling. It's just basic, the way that we do the geometry starting with postulate, right? So if you figure this out, then this is a nice plate. This is the only shape that will satisfy those conditions. It's easy, you just do a surgery. The first two will give you this, and the third one bring you out here. So this comes. So there's a margin here. The target, if I have a feature, if I have an image who is truly beyond this group, then these two features, the target feature and contrastive feature has to land on exactly on this region, nothing else. On the other hand, if this image is from the other group, then you have to land on this, no negotiation, right? So that's the ideal things that you wish to happen. But you need to find this feature still, that is where the training is doing it for you. So you use a neural net, try to find these features. 2 minutes? Oh my God. All right. So eventually that we turn this, and seems to be working out nicely. Okay, so this before training and eventually, and then we do a nice work. And you are curious what we do it. This is the molding training and this regression parameters that you have to play in. And this is the end part. This bit, I think if you're using the high quality product, the accuracy is definitely better. It's because it's assured that you already pick out the bad one. Now I still need 2 minutes, okay? Talking about this most exciting project there, and my colleague of spatial has spent at least 2 years, endless, nightless job trying to get it done. All right, so it's called artificial computer generations there. What we are doing is actually very simple. So the problem is you started from this the same framework, right? Encoder here, and then usually you got this decoders, then immediately fit into this classifier. That's what we do. What we are going to do is make things more transparent. We add this called the pinball. It actually looks like a hierarchical clustering hybrid thing. So you will start it to transform this into certain nodes, and these nodes are easier to interpret. And we sort of using this sort of the hierarchical structure. Actually, this is a very simple one. It's binary. So these two nodes will taking the maxima will lead to this node, and eventually the maxima will be representing this whole group and compete with the other class. Then you reach your final prediction. Okay, so you put into this internal logic, and the internal logic is trying to explain is that, look, I have these features, and this is another feature. Which one is the stronger features there? Using the maxima to present a lower. So this is a lower level feature. This is a higher level features. So it's a structured way of making the reasons. So people can interpret this notes now. We're not going to use this linear combination. For this linear combination is very difficult to explain. But now this one, fit well to Steve's talk. You got these features there. You just want to use it because it's easier to interpret. All right. So we have this one and we organize it in this way. And human being with that is an easier way to do it. The maxima also represented this nice thing. It's either or. If you have this feature, that's fine. If you have this feature, or if you have both of these are, those are fine. If you do not have that, sorry, you click it back to this. All right. So that's a way using the Boolean algebra. And actually, this can code many features there. And you have this up, down, and lower down situation. And then let me do it very quickly. But the question is, how did you train it? That's there. So you have to figure out a modeling plan there. So we just using this plate. This is a different plate from the yo-yo plate. Because here we would like to do this splitting. If you look upon the top down, you're actually doing this split. So you have to create this one group becomes two groups, and they have to be sitting here and sitting there. And this red part are from the other classes. They are not there. So it's an interesting design there. And all the levels, they are doing the same. All right. So my time's up, and that's my yo-yo plate, and it covers this sort of the data flow. This beautiful pictures there. You know, this is the sort of the this one is object-wise. It's just an object of yours. It looks like a correlation between us. So this one is not from the data. This is just the big one. Suppose that you're able to find these features exactly, and then this is the sort of the target you should have. But your data is a partial appear here. So the upshot of it is this: we are not representing an image with this ample feature space. Now we're representing an image using the trees. This trees there. So that's a big difference there. And I believe using the tree to represent an object is much easier for you to make a logical decisions there instead of talking about where I'm looking at. I'm going to look at very subtle pictures or a very broad view of that. In computer science, is debating against them. A lot of times, where this one is actually capture the subtle features or on a higher level feature. There's no definition of that. I don't think there will be one. But this one, we still do not know what these roots are really, but it's open to the interpretations there. But at least logically, logical operation is quite clear. All right, and so I'm going to skip this. It's about the application, and you can see that we also use this UMAP to find what is the impact on this. But this is just for fun because we are replacing this by this the trees now. It's more structures rather than this. This one also fine. You can see the manifold to figure out, but still. Okay, so that's what I'm going to do. It's just some pictures which has particularly strong on each root, and some picture are kind of in combination. On my card, Ker-Chau has now becomes an expert. You can tell this picture and tell me, oh, this one is tumor and that one is not. Just by training of his movement. Yeah, so All right, this is the activations. People talk about on this image level, which one are activate, and this is actually doing that. But well, this is a software available. You can plug in. All right, final thing. I'm wrapping up. ChatGPT to give some reference, and they have it. And this one is they gave it. If you're interested, look at it, but don't. The first two are fake. They are ghosts. Okay, the real one is I just do my own craft, and this is the real reference. Yeah, so don't trust Gemini's there. They can produce something wrong, although it's helping a lot, no doubt about it. I will not be able to deliver this lectures without Gemini's help, right? Because there's tons of literature out there in this AI world. You just impossible to digest there, but it's a great tool, but reliability is the issue. So let's back to my first slide there. This so the quality control, that's the issue, and we have to do it. Right.
Just a few questions.
Well,
you're using a binary tree. Have you considered using other types of trees, like for example, more leaf, like more nodes?
No, we don't want that, and we are against that.
Well, what about things that don't have a binary tree structure?
We don't care. Because we just state on the ground that we are going to do it in this operational research way. Say, suppose now you have a warfare. There's no room to negotiate. You just follow this order, because that's the way this operation logic is doing it for you. All right, and that's the way we want to enforce. Right, some data may not be doing that well, but we believe a lot of data, you use that, it's going to be a very good way to replace your original ample ways there. Now, why we do not want to be too loose? Because I want to encourage you guys to do it for me. My brain and my colleague's brain is only structured, very well structured. It's just binary, and that's the way we are able to train it. You can say that we want to this and that, but training is a big issue there. So here, we spend a lot of time trying to design that plate so that you can train the computers to have that features we will set up. All right, so it's a very rigid mechanism. So that's back to my overtone there. I used to be trying to look at the data and see what's in there. I don't think it's going to work. So now I'm going to be force the orders there, force people to think about this way. So you have this very nice full trees there that's serve as your embedding space there. So we are embedding things on this sort of R to the P Euclidean space. We are embedding things on this binary tree, regular binary trees there with different levels. So that's your starting up. And your data will be a distribution on this binary tree. And then you can try to use a lot of technology, try to characterize what's the difference between that, and that's easy to go. All right, so that is our strategy. But you have another set of the system there, welcome to do it. But the argument here is that, and that's actually quite important, you need to set up the geometry first. You want to use the Euclidean geometry, you use the other or certain manifold, simply spread it out without looking at the data. And then you can embed it here. So this is the different philosophies we're trying to do. So that's a lot of things. And plasticity, that's the key. All right, you can always grind it out. So you want to use this sort of, say, crime battle, try to, as your representative group, welcome to do it. You can, train it so the data will be fit well. There's tons of the new properties will coming out because this crime is inside and outside there. Nobody really knows that. Yeah, it's a lot of fun there. Yep.
So pathologists are people who train themselves looking at such images for a while, and they have their own ways of doing what you're doing there. Have you asked any pathologists what they think about the nodes of your tree? Can they say, oh yeah, that's this, or oh yeah, that's that, or is it completely orthogonal? Well, I'm very curious.
That's the what we do have tested to many pathologists.
Oh.
But He-Hao, the leading author, his roommate is a physician and he's a pathologist. And he got the lessons from him how to identify it. So to some extent, it's interpretable. Okay, so that part is not an issue. Just very much like you're saying. If you look at the very extreme case, usually it's very clear cut. Yeah. But if you look at something in the middle, even a pathologist has a hard time because different ways.
You look at your dichotomy, your tree. Pathologist doesn't find it very interpretable. Or coarse scale, of course, but fine scale is not so useful.
Fine scalable.
The difference between these two nearby nodes.
If it's between the two, yes, they know what it means. Yeah. The thing is that if you got a little bit longer distance there, then that's hard. All right, it's multiple things, but if we just have this unique trees that, unique roots, right? Pick up this root there and this one, these are so separate and they are unique, all right? And those usually represent a very distinct constructive image-wise, just like you were trying to show there. Yeah, those extremes are easy. I think because we actually original design is to find those unique root trees there, but we find that's impossible because the words are not that simple. Think about you build a car. People initially have this idea of what car should be, but eventually it diverges there. So you get the idea here and idea there, and so how you do this organization. So there's no logical way to organize it, all right? But we're still trying to have some. So that
binary trees have the property that you can flip any two, and it's still the same tree.
Right.
But when you're trying to think of ordering things, that can make a big difference. Have you thought about how?
No. This is just it really does not matter. Well, in terms of this final vertical one, it does make a difference there. But we try to do a little bit careful thing so that you would not have the two something to sort of abruptly change or something, right? So we still maintain certain order there. Left and right, of course, is a problem. But our left and right is stick with the original, when you have this original tree. There, you have to put the order there. So that order is arbitrary, but we just set there. It really doesn't matter. But on this vertical one, then you have to consistent with that order. Otherwise, you're causing a problem. Yeah, it's a good point.